In this video, we're going to look at applications that will involve using partial derivatives. Partial derivatives will appear in a huge number of real-world problems, and that's just because in the real world, we work with rates of change in systems that involve multiple variables or constraints. And if those variables or constraints change, everything else will change as well. Now, don't forget all of the differentiation techniques that you've already taken care of learning, like implicit differentiation. You may want to brush up on that because they will still work when I'm doing partial derivatives. So real-world examples that involve partial derivatives can be approached in two basic ways. One is to isolate the variable you're taking the derivative of, and this can be a very straightforward process, or you can have a function that makes it extremely difficult and risky to try and isolate that variable without making any mistakes. So if you can't isolate the variable easily, you can always take the second approach, which is to use implicit differentiation. So let's work an example. The law of cosines can be written as c squared is equal to a squared plus b squared minus 2ab times the cosine of theta. Now for all triangles where theta is pi over 3, we can get a function c that is a function of a and b, where a and b are both greater than 0. So what I want to do is assume that theta is pi over 3 and compute the partial derivative of c with respect to a and the partial derivative of c with respect to b using the process of solving for c and then doing the differentiation. Then I want to compute the partial derivative of c with respect to a and the partial derivative of c with respect to b using implicit differentiation. So in the first case, I'm simply going to isolate c. I need to plug in pi over 3 for theta, and cosine of pi over 3 is 1/2, so that my function c is given by c is equal to the square root of a squared plus b squared minus ab, where I use the positive principal square root. Now I'm simply going to take the partial derivative of c with respect to a. I do that by treating b as a constant. My partial derivative of c with respect to a becomes the quantity 2a minus b divided by 2 times the square root of a squared plus b squared minus ab. The partial derivative of c with respect to b is given by the quantity 2b minus a divided by 2 times the square root of a squared plus b squared minus ab. This is isolating c and taking the partial derivative with respect to a and b. Now I want to compute the same partial derivatives, but use implicit differentiation instead. What this means is instead of taking the square root of both sides to solve for c, I'm simply going to use implicit differentiation on both sides of c squared is equal to a squared plus b squared minus ab. The partial derivative of c with respect to a on the left will give me 2c times the partial derivative of c with respect to a, which is equal to 2a minus b. Notice that my b squared is handled as a constant here, so it just has a derivative of 0. Now I'm going to divide through by 2c, and I find that the partial derivative of c with respect to 2a is given by the quantity 2a minus b over 2c. Now I'm going to do the same thing, but take the derivative with respect to b. On the left, I get 2c times the partial derivative of c with respect to b is equal to 2b minus a. I divide through by 2c, and the partial derivative of c with respect to b is the quantity 2b minus a over 2c. This does not look exactly like the result we got in part A when I solved for c and took the partial derivatives with respect to a and b. But keep in mind, c is equal to the square root of a squared plus b squared minus ab, which means that the partial derivative of c with respect to a in this case can be rewritten as the quantity 2a minus b over 2 times the square root of a squared plus b squared minus ab, and the partial derivative of c with respect to b can be rewritten as the quantity 2b minus a over 2 times the square root of a squared plus b squared minus ab. Now my result is identical to what we got before. So both methods work and they give the same result. Now let's work another example. I want to start with the formula for the volume of the cap of a sphere of radius r and thickness h. And this formula is V is equal to pi thirds times h squared times the quantity 3r minus h. And this is for 0 is less than or equal to h, which is less than or equal to r. Using this formula, which gives me a volume as a function of r and h, I want to compute the partial derivatives vh and vr. And then, for a sphere of any radius, I want to know if the rate of change of the volume with respect to r is greater when h is equal to 0.2 r, or is it greater when h is equal to 0.8 r. And finally, for a fixed radius of r, what value of h, provided that 0 is less than or equal to h, which is less than or equal to r, is the rate of change of volume with respect to h the greatest? So in the first case, I'm going to compute the partial derivatives vh and vr. In order to make this a little easier, I'm going to distribute the pi thirds h squared into my parentheses so that my volume expression becomes V is equal to pi h squared r minus pi over 3 h cubed. Now my partial of V with respect to h is given by 2 pi hr minus pi h squared. I can write that a little differently by factoring out the constant pi, and I get pi times the quantity 2rh minus h squared. Vr is the partial derivative of v with respect to r, and that just becomes pi h squared. This is because pi thirds h cubed is a constant, so that derivative goes to 0. Now, assuming a sphere of any radius, I want to know if the rate of change of volume with respect to r is greater when h is 0.2 r or when h is 0.8 r. The words rate of change of volume with respect to r in that statement tell me that I need to use the partial derivative of v with respect to r, which is given by pi h squared. I'm going to plug in the two different values for h and see which is larger. So vr evaluated at 0.2 r gives me pi times 0.2 r squared, which is equal to pi times 0.04 r squared. And then vr evaluated at 0.8 r gives me pi times 0.8 r quantity squared, which simplifies to pi times 0.64 r squared. Pi times 0.64 r squared is greater than pi times 0.04 r squared, so that the rate of change of the volume is greater when h is 0.8 r. Now I want to determine the value of h when h is between 0 and r with a fixed radius, where the rate of change of volume with respect to h will be the greatest. Rate of change of volume with respect to h tells me I need to use the VH derivative. So VH is equal to 2 pi HR minus pi h squared. The maximum value occurs when the derivative of the function I'm maximizing, VH, is 0. So I have to take the derivative of VH now. The derivative of VH with respect to h simplifies to 2r minus 2h. I've just divided through by my pi value. I add 2h to both sides, divide through by 2, and I find out that when h is equal to r, I will get the maximum rate of change in the volume with respect to h. Now you get to try it. If the volume of a box with a square base of length x and a height h is given by v is equal to x squared h, then pause the video and find the partial derivatives of v is equal to x squared h, then determine what the change in volume for a box with h is equal to 1.25 meters will be if x increases from 0.5 meters to 0.52 meters. When you're ready, restart the video to check your understanding. So in this case, I know that my side length of the square base is x, The height is h, so that my volume is v is equal to x squared h. I want to set h at 1.25 meters and determine how much the volume will change if x is increased from 0.5 to 0.52 meters. So I start by finding the partial derivative of v with respect to x, which gives me 2xh. And then I find the partial derivative of v with respect to h. This gives me x squared. Delta v is approximately equal to 2xh times delta x. This is what we're going to use to determine this change in volume. That means my change in volume, delta V, will be given by 2 times the original x length, 0.5, times the height, 1.25, times the change in x, 0.02. The change in volume as x goes from 0.5 to 0.52 is equal to 0.025 cubic meters. This is how we use partial derivatives to analyze and solve real-world applications that involve two independent variables. Be sure and let me know if you have any questions.